Flat presentation number 2.
So in this experiment, we studied the motion of a glider on an air track using a motion sensor and a PASCO capstone.
Main objective was to analyze the glider position and velocity as it moves back and forth along the track.
This was to understand how direction and magnitude affect velocity in a one-dimension motion.
In this video, we will walk you through our channel, procedure, data analysis, and finally our conclusions.
Now, equipment setup. Glider. Purpose. The object whose motion is being studied. Function. It slides almost frictionless along the air track thanks to the air cushion, so you can study uniform motion, acceleration, or collisions under nearly ideal conditions. Air track. Purpose. Provides a low friction surface for motion experiments. Function. Air escapes through tiny holes in the track, lifting the glider slightly to reduce friction, stimulating near frictionless motion. Motion sensor. Purpose. It tracks the position, velocity, and acceleration of the glider continuously. It functions sends ultrasonic pulses that reflect off the glider and measures the return time to determine real-time motion data, using graphing position versus time and velocity versus time.
Before we started, we made sure the air track was balanced. We placed the glider in the center and turned on the air pump. If it stayed still, the track was leveled. If it slid, we adjusted it until balanced.
We then connected the motion sensor to the computer, opened PASCO capstone, and set up the position versus time graph. The sensor was aligned to see the glider for its entire motion.
Our group selected the graph as our model, where the glider moves toward and then away from the sensor, creating a triangular.
For the experiment development, we performed the experiment by gently pushing the glider along the track. The motion sensor recorded the position over time, and PASCO capstone generated a graph.
In the coordinated tool, we selected 3 points of the graph. Initial position, change of direction, final position. Initial position would be 0 seconds and 0 meters. Change in direction would be 4 seconds and 2 meters. Final position is 8 seconds, well, 1 meter and 8 seconds.
So then we labeled section 1 as going away and section 2 as going point.
Data processes and analysis. Next, we calculated the velocity using the formula v is equal to final position minus initial position divided by final time minus initial time.
So for the second table, to point A to point B, it will be changing position 2 meters, time for 4 seconds, and velocity for 0.5 meters per second. And the point B to point C, it will be -2 meters, changing time 4 seconds, and velocity -0.5 meters per second. So now it's time to answer these 3 questions. How the line looks when we increase our y-axis value. When the y-axis value position increases, the line slopes outward from left to right. This positive slope indicates that the object is moving in a positive direction away from its starting point. In this specific graph, it seems in the first 4 seconds where the line rises steadily from 0 to 2.0 meters. Second question, how the line looks when we decrease our y-axis value. When the y-axis value decreases, the line slopes downward from left to right. This falling line represents a negative velocity, meaning the object is moving back toward the origin or in the opposite direction. My graph shows this behavior between 4 and 8 seconds, where the position drops from 2.0 meters back down to 0. For the third question, how the line looks when the y-axis value stays steady? When the y-axis value stays steady, the line appears perfectly horizontal or flat. This means that as the time passes, the position remains constant, meaning the object is at rest. My graph does not have a flat section. A horizontal line at any height will represent velocity of 0 meters per second.
The opposite sign shows a direction change, but the magnitudes are nearly equal, meaning the glider speed was almost the same both ways. We also compared our computed values with the capstone velocity graph, and they matched close.
Now for step 4, first I went to the capstone software and changed the graph settings from position to velocity so I could see the actual motion data. Then I looked at the shape of this new graph to see how well it lined up with the horizontal lines I predicted earlier. In my report, I make sure to describe any differences I noticed, like if the lines weren't perfectly flat or if there was noise in the data. Next, I used the highlighting tool to select all the data points from the first part of the glider's trip when it was moving towards the sensor. I clicked the statistics icon to find the mean, which gave me the average velocity for that specific time interval. I recorded that value in my table and I took a screenshot of the graph with the stats box visible to include in my report. Finally, I just repeat those same steps for the second half of the trip to get the average velocity for the glider moving away. For the line from point A to point B, the mean velocity, we got 0.43 meters per second from the computer. And then from the hand computed velocity, we got 0.412 meters per second. And then we did this operation to get the difference, that it was value 1 minus value 2 over value 1 times 100, and we got 4.19%. And then for the point B to point C, we got the mean value from the computer, negative 0.37 meters per second, and the hand computed velocity was negative 0.359 meters per second. And we again did this procedure. So overall, the summary is that the first graph shows the glider strip as a steady back and forth movement and forming a clear V shape. It starts at the origin and moves away from the sensor at a constant pace until it reaches the 2.0 meter mark. And at that point, it immediately reverses direction and travels back toward the sensor at the same steady speed. And because the lines are perfectly straight rather than curved, it proves the glider wasn't speeding up or slowing down during the segments. It was moving with a constant velocity. We've been waiting for so long. We've been waiting for this time to. And finally, your takeaways that the first one is that slopes reveal direction. When the line of the graph points upward, the glider is moving away from the sensor, and when it points downward, the glider is moving back toward it. And the second takeaway is that the peak is the turning point. The highest point of the graph at the first seconds marks the exact movement the glider stopped moving away and reversed its direction. And speed versus velocity, even though the directions change, flipping the velocity from the positive to negative, the steepness of the line stayed the same, and this means that the speed was identical both ways, just in opposite directions. And the last one is that it was uniform motion. Since the lines are straight, we know the glider was in uniform motion for each segment, meaning it maintained a steady pace until it hit the turning point.
Attention, this was our last presentation on glider motion and an air track. Credits: Screen, Perla, Abigail, Moises, and Omar. Calculations, Moises and Omar. Video editing, Perla and Abigail.